whether it is force, whether it is electric field, whether it is potential, whether it is right. So different kinds of parameters we calculated, and we also saw that when we connected, so when we connected the battery and we placed, and when we placed the dielectric, then all the things got increased by k amount of time by that dielectric constant, right? And obviously the potential and electric field was constant. And then what did we do? And then we disconnected the battery, right? And then we saw that all the things except this capacitor got decreased, right? Voltage, electric field, and the energy stored, these got decreased by the amount of dielectric constant, right? So, and then we did this numerical. So now, today let us do this question and then we'll move on to the heat dissipated and sharing of capacitance. So, but before I do that, do you guys remember if this is an electric field? If this is an electric field and I put a charge over there, so what would be the force experienced by this charge? Yeah, so QE, right? So QE and in this direction. Good, Shah. So this would be the force, right? And if charge is negative, then the force would be in the opposite direction. So this, keeping this in mind, let us solve one question. So the question is that a charge or an object of mass m and charge q is placed between a parallel plate capacitor, right? Find the time period of oscillation of the object if the length of the string is L, right? So we have this right thing, and on this some charge is hanging, and it has, so this has some charge q and some mass m, and this is placed between the dielectric, or this is placed between the parallel plate capacitor. This is positive and this is negative. So this is right. Okay. And we have to calculate that what is the time period of oscillation of and the length of this is L. Okay. So we have to calculate what is the time period of oscillation. And if you guys already know, so can you guys tell me that if I have if I have a bulb, of mass m, and it has the length of the thread is L. And if I take this bob of mass m in here, right at this extreme position, and I just leave, so this is the extreme position, but let's say that I take it in here and I leave this bob. Okay, so this will come at this point, it will go here and then come again in here and then come and then will go here, right? So it will oscillate. So this is this case of a simple pendulum, right? So can you guys tell me what is the time period of oscillation of a simple pendulum? What is the time period of a simple pendulum? Do you guys remember? Yes. So pi omega. Yeah. Time period is 2 pi omega. We know that because angular frequency is t. Omega is 2 pi by omega. So 2 pi omega. Because omega is 2 pi by t, right? This is angular frequency. So angular velocity is 2 pi distance by time. So t is 2 pi by omega. And this is 2 pi mu, or omega is 2 pi. So this omega is 2 pi, right? But I'm asking that I'm asking that what is the time period of oscillation in context of gravity? Simple pendulum. This is not a circular motion. For circular motion, this is omega is 2 pi by omega. Okay. I'm asking about this simple pendulum. What is the time period of oscillation? So this is, do you guys remember now? Yes. Do you guys remember now? This is the time period of oscillation, right? In terms of gravity. Yes, guys, understood. Yes, Shavez and Tariq. Now do you guys remember this time period of simple pendulum? I guess you guys now. So, so keeping this in mind, now the only force that was acting on this simple pendulum, right? So only force on this simple pendulum when it was in this position, right? So this was only mg. In here, this was only mg, and in here, this was only mg, right? So for this case, we found the time period to be 2 pi root L by G for this case. Okay, now we have a simple pendulum, but it is kept between the two plates. It is kept between the two plates. And now we have to find out what is the time period of oscillation, right? So this time period will be changed to 2 pi root of L by G effective. And what is this G effective? Because there would be a net force acting on this object, right? So there would be some net force, and what would be the net force, guys? Because in this object, there were only gravity in the downward direction. But this object is charged with some charge Q and it has some mass. So if has some mass, then it will have some weight, mg. And what would be the other force? Chavez and Tariq, what would be the other force? Yes, what would be the other force? Hmm. So, can you guys tell me that if I have a parallel plate capacitor, so what is the electric field inside the parallel plate capacitor? What is the electric field? Chavez, so this question we have done so many times. Chavez and Tari, what is the electric field inside the parallel plate capacitor? This we have calculated. Yes, guys. Oh, this is not positive. This is negative. Yes. Remember, or you guys have forgotten? Yes, Tarif and Chavez, are you guys listening? Hello, are you guys there? Or you guys have gone somewhere else? Are you guys listening, Tarif and Chavez?
Yes, sir.
Yeah. So I'm asking that what is the electric field between the plates? This you guys have to. So this is a CBSE question, right? We have calculated when we calculated the capacitance of the parallel plate capacitor, we talked about the electric field between the plates. Okay, so just to recap you guys, that outside is sigma by epsilon. Yes, so sigma by, yes, sharp. So we have a net electric field in this direction, which is sigma by epsilon naught, right? And outside is zero, outside is zero. Inside, in this direction, we have net electric. Okay. So now we have this parallel plate capacitor. So it will provide a net electric field in this direction, right? So due to this net electric field, this charge will experience a force, and that force would be in this direction, right? So that is QE. Okay. So now we have a net force. And can you guys tell me what would be the net force? So we have this is QE, and this is mg. So can you guys calculate me the magnitude of the resultant force? Please calculate and tell me what would be that. Remember, these are perpendicular. Yes, guys, please calculate the
Sir,
magnitude
will
of the
it be zero?
zero.
Yes,
So
sir.
what is balancing this F net is 0. So is this QE balancing this? Do we have something like this which is balanced? Do we have any
Yes, sir.
equilibrium, something like equilibrium?
Yes, sir.
We don't have, right?
Yes, sir.
Because these are acting perpendicularly. So let me ask you a question like this. Let's say you have a vector A and you have a vector B. So what is the resultant?
A plus B.
Yeah, so net is, let's say R, this is A square plus PS Shabir, you are right. So 2AB cos theta. This is the net resultant, whatever resultant of these two vectors, right, from the parallelogram's law. And the angle between A and B is how much? Theta is 90, so this part is 0. So we only have A square plus B square. Similarly, F net is root of mg square plus qe square. Right, guys? Is this part clear? Clear is this part. So
Yes, sir, clear.
we will have an F net, right? We'll have an F net in this direction. So this is F. Okay, good. So now this F net is providing the acceleration. So can you guys tell me what is the second law? What is the second law? How force is related by the second law of motion?
Can you repeat?
Yeah, so force is related by something in the second law of motion, Newton's second law of motion. What does it say?
Newton's second law of
Yes, first law is law of inertia, right?
yes, sir, law. Second is
Second,
friction.
second is friction. Do we have any friction in Newton's second?
No, so the F is equal to MA.
MA, right?
Force. Yes,
Yes,
sir.
yes, right, right. That is the Newton's second law. So F net would be equal to MA, right? So this is root of mg square and plus qe square. And remember what we need to calculate. We need to calculate the acceleration, net acceleration, right? Net acceleration we have to calculate. So this has some net force. In the simple pendulum case, the net force was downward only. But in this figure, we have a net force which is in this direction. So due to this net force, we don't have only g, we have net acceleration. So that we have to calculate, and let's take this m in the inside of the root. So this would be m square g square divided by, if this m goes inside the root, what will it be? If I take the m inside the root in the denominator, so what would be that?
Can you repeat?
Okay, so let me write one step and then I will take it inside. Okay, so this is, so if I take this m inside the root, what will happen? So what would be the first term? If I take m inside the root,
M square G square by M plus QE square by M.
m. So this is,
Yes, sir.
remember, this is root. So
Yes, sir. Root 2M.
so you are taking inside. Okay, so
Yes.
let me ask this question. Let me ask you this question. So I have this 1 by m square. And if I take it outside the root, what I will get?
So can you repeat?
I have root of 1 by m square. So if I take it outside the root, what will I get?
1 by M.
1 by m. So if I ask the question reversely, backward, if I take 1 by m inside the roots, what will be there?
Yes, M2 G2 by M square.
M
Then,
square, right? Yes, absolutely right.
Then plus QE square the whole square by M square.
Yeah, so let me write it this. Okay, is this clear? So this part cancels, and we have A, which is G effective. So this is G square plus QE by M whole square. So this is my G effective. Okay. So my time period would be how much? Time period of oscillation, this would be 2 pi root of L by G effective, which is 2 pi root of L divided by, let me write it in power half. So G square QE by M whole square and power half. Is this part clear, guys? Is this part clear?
Yes, sir, clear.
And if you see, do I get the conventional solution or not? So if I have electric field which is zero, then what will I get? I will get this part is zero. This is G square power 2, power 1 by 2. So I'll get 2 pi root L by G. I'll get back the standard solution of simple pendulum, right?
Yes.
So yeah, so you guys, if you guys have any doubt, please ask me, or then please note down this problem. Okay.
Will these questions come for you?
Yes, this question is,
Will these questions come for you?
yeah. So this is in one of the papers of the JEE. So that is why I
Okay.
did. Yeah, that is why this question has been asked in JEE. And there is a similar kind of question, so that I will give you guys as a homework. So you guys please try that question. Yeah, whenever you guys want me to scroll down the screen, guys, please tell. Okay, so done. Okay, then please note down. Whenever you guys have noted down this part, please tell.
So why did you take mg? Why did you take mg whole square?
Yes, why did I take mg equal to
No, so why did you square mg? Not
mg
q.
square? Oh,
Yes, sir.
okay. So I can write it as q square. Okay, so I can write it as q square e square by m square, right? So I can write it like that. But
Yes, sir.
this as a whole is up for a second. Oh, yeah. Okay. Oh, Shaved. Still up. Oh, sorry. Why did you tell me? So, yeah, this one. Is this okay, Shaved? Yes.
So this is based on simple pendulum.
Yeah, which one is?
Is this based on simple pendulum?
Yeah, this is based on simple pendulum. So when we don't have any external electric field, then what does the simple pendulum do? So this you have done in your experiment class, right? In maybe in your 11th class. So you put so you have this bob of mass m, right? And this is hanged by some thread, let's say S. So when you place or when you take this bob of mass m in here, so right, then okay, so then what happens? Then you release this bob. So it will go down, right? Due to this gravity, it will go down, it will reach here, and then it will again go in this direction. So it will go like this, right? So this is what the simple pendulum, simple harmonic motion, right? Understood?
Yes, sir.
Yeah, you guys please note it down, and then we'll do the sharing of capacitor, heat dissipated in capacitor, and all those sorts of questions. Yes, whenever you guys need me to scroll down the screen, guys.
So can you scroll down?
Yeah, this part is. Yes, whenever you guys have completed this. Okay, so Chavez has completed. Sorry, what about you?
Yes, certain.
Okay, so now let us do some simple questions. That we are still in capacitance. So now, heat dissipated in charging of a capacitor. Let's say that initially we had a capacitor. So this is not charged, right? So this is the initial. And then what do we do is that we connect to a battery of, let's say, EMF E. So this is EMF E, right? And we connect this battery. So this battery charge this capacitor, right? And it has, so this has capacity and this has this. So the question is that how much heat is dissipated, right? How much energy has been lost, right? My voice is low. Mm, am I clear now? Am I clear now, Chavez? Yes. Am I clear now? Okay. So the question is that initially this capacitor was uncharged, right? Now what you do is that you connect an EMF to this, connect a battery of EMF E to this capacitor and you charge this capacitor. So this is your final stage. So this is initial stage and this is the final stage. So you have to calculate that how much energy has been lost or what amount your heat is dissipated, right? So some amount of energy has gone to this capacitance, charging the capacitance, and some amount has been dissipated in the form of heat. So we have to calculate this heat dissipation. So to do that, what we will do is that We will first calculate the change in charge. So initially, what was the charge? What is the charge in here? Remember, this is an uncharged capacitor. So initially, the charge is zero. Right. Now, final charge is how much? Final charge is how much? So capacitance is C. Absolutely right. So this is CV, which is CE. Okay. So this is the final charge. And if we calculate the change in charge, right, this is how much? This is Q final minus Q initial. So this is CE minus 0, which is C. So now we want to calculate how much work has been done to charge this much. So we know that work is how much? Work is potential delta Q, right? So potential is E and then delta Q is C. Okay, so this is CE square. So this has been the work done, right? But what is the energy stored in this device? What is the energy stored? So what is the change in energy? Initially it was zero. So what is the energy stored in this device? How much is that? Can you guys tell me? Energy stored in the final state. Yes, guys. Half CV square, right? So half CV square. Absolutely correct. Yes, correct, Shah. So half CE square. So CE square by 2. So you guys can see that the battery has done this much amount of work, but you can see that efficiency is not 100%. So this amount of work has been done, but it has not, the total work done has not been converted to the energy store, which means that some amount of work has been wasted, right? Some energy has been lost, and that energy has been lost in the form of the heat. So that is why you must have seen in some devices, these devices got heat up, right? So the device gets heat up because of the energy wasted, right? Energy dissipated. Okay, because the whole energy is not converted, the whole work is not converted to the energy, right? So if we calculate the heat dissipated, let's say H, so this would be work done minus energy. So this is CE square minus CE square by 2. So this is CE square by 2. This is the heat dissipation, right? So can you guys, so this you can see that H is CE square by 2, right? Which is 50% of the total work done. So this means that 50% of energy is lost in heat, in the form of heat. Okay, is this part clear to everyone? Is this part clear?
Yes, okay.
Okay, so we'll do one question based on this, and then we'll study about sharing of capacitors. So you guys please note it down, and then we'll do the next. So when you guys want me to scroll down the screen, guys, this is looking like a theta. So whenever you guys want me to scroll down the screen, guys, please tell me.
So can you scroll down?
Yeah.
So can you explain the delta U part?
Yeah, can I what?
Can you explain the delta U part?
Delta U. So that is the energy stored, right? This much amount of energy is stored. So that is half CV square, right?
Yes, sir.
Yeah. I'm writing it delta U because initially what was your energy stored? It was half CV square, but this was zero, right? So this is zero. And finally, your U final is half CV square, which is half CE square. So that is why I have wrote this as delta U, right? So change in energy. Yes, whenever you have completed this part, please tell. So, did you understand this part? Why did I write this delta U? Sorry. Yes, sorry. Did you understand that part? Yes, sorry. Are you there? Done. So Chavez has noted. Tari, what about you? Yes, Tari, are you there? Noted. Yes, Tari, are you around? Where, where have you gone? Yes, Tari. Uh, okay, so yeah, Tari, are you there? Can you hear me?
Yes, yes,
Yeah,
yeah.
yeah. So let me explain this again to you that
Yes, sir.
yeah. So did you note down this whole part?
Yes, I'm noting it down.
Or you are still noting it down? So let me again explain this to you that we had a capacitor, right? This was not charged, but you added or you connected a battery to this capacitor to charge this device, right? This capacitor. So
Yes.
there has been some total work done, and this work done was done to change the energy storing capacity of this device. So first, what did you do? You changed the energy storing capacity of this device, and then some work has been done, or some work has been done in the amount of heat released. So the total work done is used to change the energy storing capacity, and then some heat is dissipated, right? So that is why I'm writing it as delta U, because initially it has some energy storing capacity, but this work changed this capacity to this much, right? So U final, U initial. That is why I'm writing it delta U, and some heat energy is also lost. So that is what we mean by this delta U. Understood?
Yes, understood.
Okay, so whenever you have noted it down, please tell. So we'll do some question, and then we'll study about the sharing of capacitor. So in this example, we had only one capacitor, and we were charging this capacitor. But in the second case, we'll see that what happens with the two capacitors. Whenever Tariq, you have noted it down, please tell.
Yes,
So
sir, noted.
is this class till 10:30? Yes, Chavez. Uh, do you have to go somewhere else? Yes, Chavez. Is there anything that you want to say? Yes, Chavez. Oh, you have to go for Salah. So, okay, so at 10:15 I will stop this class because Madiha is not here and Faiza is also not here. So then we can keep this class short, right? Because otherwise they will, yeah, so they will miss some important topics. Okay, so let us do this problem and then I'll stop this class. Okay. So we have a question that a capacitor initially was charged, a capacitor of capacitance C, right? Initially was charged to E voltage, and then it is connected, it is connected to an to a battery of EMF E by 2, right? So this is the question. In first case, we have to find that total charge flowing through battery, right? This is the first question. Then we have to calculate work done in the process, work done by the battery, let me say, by the battery. And lastly, heat dissipation. These are the three questions that we have. So let us write down the initial condition. Initial stage is this is charged, right? And this has capacitance C and EMF E. Okay. Now what you do is that you connect this capacitor to an EMF of E by 2. Right. So now this is capacitance. Okay. So the first question is that what is the total charge flowing through the battery? So first, initially, what is the Q initial? What is the Q initial? Tarif, what is the Q
Yes.
initial? Q initial, what is?
Q final minus
No. Q initial. Initially, what is?
0.
This is charged, not
Yes,
uncharged. CV.
initial. Yes, E sigma by E naught.
CV, right?
Yes,
Charge is C. So C and EMF is E. So C. Yes, correct, Shadu. So this is Q initial, right? C. Okay. Now, can you tell me what is Q final?
1
Sorry,
1 by CV.
1 by? So charge is always CV, right?
It's a half CV. It's not. It's half, right? Fine.
CV. Charge is always
Okay.
CV, right? So C is C and B is how much? E by 2. Yes. So CV by 2. Yes. So CE by 2. Right? Is this part clear,
Yes.
Tariq? So now, whatever there is a change in charge, that has gone to this battery, right? So the change in charge, so the charge flowing through this battery is change in this charge. So total charge flowing through the battery is Q final minus Q initial, right? So this is CE by 2 minus C. So this is minus CE by 2, right? Is this part clear? So this is first part. And the second part, we have to calculate work done by the battery. So work done is how much? W is voltage into charge flowing through the battery, right? So this is voltage is how much? Voltage through the battery, voltage through the cell. What is that? How much is that? Sorry, Chavez.
As CE square.
So E by 2. E by 2 is the voltage,
So CE
right?
by 2.
E by 2. E by 2. Voltage is E by 2, right? Not the delta Q. So you are telling me delta Q, but I'm asking this voltage. Voltage is E by
Yes,
2, right? E by 2, right?
CE by 2.
So E by 2 and then delta Q. So now delta Q, as you are saying, this is CE by 2. So the work done by the battery is CE square by 4. Understood?
Yes, sir.
Now what would be the heat dissipated? Remember, heat dissipated is work done minus delta U. So how much is delta U? Remember, in this case, U initial is not 0. How much is U initial?
You initial. So can you show the type?
Yeah, so U initial is how much?
You initial E.
What is the energy stored in the capacitor?
CV.
Half CV square, right?
As a half.
So half CE square.
Yes, sir.
So U initial is half CE square. And U final is how much? So let me write it.
CE square.
So again half CV square.
As a half.
So let me write it in here. So U initial is half CE square and U final is okay. So yeah, so you are telling me the change in it. Yes. So half C and E by 2 whole square, right? So half of, and this is 2 to 4, so this is 8 CE square. Yes.
Yes, okay.
So U final is C square by 8. So CE square by 8. So what would be the delta U? U final minus U initial. So CE square by 8 minus of CE square by 2. LCM is 8, right? So this is CE square minus of this is 4. So 4 CE square. So this is minus of 3 CE square by 8. Clear?
Yes, sir.
So now we have to calculate the heat dissipated. So heat dissipated is work done by the battery, which is CE square by 4. So minus CE square by 4 and minus of minus 3 CE square by 8. So this is minus CE square by 4 plus 3 CE square by 8. What is the LCM of 4 and 8? This is 2, 4, 2, 1, 2, so 8. This is 8 and this is minus 2C E square and then this is 3C. So heat dissipated is C E square by. Is this part clear, everyone? Any doubt? Yes. Any doubt, guys?
Can you explain the last step?
Last part. So this part.
Yes,
This
sir.
is 3C square minus 2C square. So 1C square, right?
Yes, sir.
So the concept of this question was that there was some there was some energy stored in this device, right? And when you connected a battery, so this battery did some work, and then it changed the energy stored in this device. So there is some energy change in internal energy or change in stored energy, and some amount of heat is dissipated. So your work done is some amount of heat dissipated plus the change in energy stored. Again, the same scenario. So that is what we calculated the heat dissipated as W minus delta E, right? So you guys please note it down, and then I will end the class. Okay. Please note it down. And Chavez, because Madhya and yeah, Madhya and Faiza are not here, so that's why I'm ending this class at this point. Because in the next time we'll extend, right? Okay, so yes, whenever you guys want me to scroll down the screen, you guys tell me.
So can you scroll down?
Why I'm writing it as theta. This is looking like theta. Okay, so scroll up. Is this good, Chavez? Is this okay? Little up. Okay. Is this part? So this we have come back to the question. Yes. So whenever you guys want.
So can you scroll down?
Okay, so Chavez, yeah, I want to take the screenshot. So just for Chavez, I am putting down the screen, and then Sarif, you note it down. Okay, so taking the screenshot, Chavez. Okay, so did Chavez go? Okay, Sarif, so you please note it down.
So can you start?